Okay, so we are going to work on section 3.4. And the first problem that we're going to look at, this will be one of the early homework problems, is they're going to give you a polynomial, which we're going to say is f of x equals 6x cubed plus 13x squared minus 14x plus 3. And they want you to factor this given the graph. So what you're going to do is, we graphed this in Desmos, so this is what the graph of this expression looks like. And what you're going to do is, instead of making the P over Q list with synthetic division, you can look at the x-intercepts, and those x-intercepts will tell you numbers that should work with the P over Q. So like if we look here, the x-intercept here we have is -3. So instead of doing P over Q and like we did back in section 3.3 and trying to factor, we're going to say from the graph, -3 was an x-intercept on the graph. So when I do -3 with synthetic division, that one should work out and give me remainder 0. And then once I found that one, I can factor the remaining stuff. So I'll bring down 6. -3 times 6 is -18. 13 take away 18 is -5. -3 times -5 is +15. -14 plus 15 is 1. -3 times 1 is -3. Those add up to 0. So we got the remainder 0 we wanted. This is no x's number. That's x to the first power. That's x squared. So my factorization, since I had -3, that creates an x plus 3 factor. The remaining stuff is 6x squared minus 5x plus 1. So to finish this example out, where we want to fully factor stuff, and you'll have a homework problem like that, I think, where they want you to factor something and they give you the graph. Look at the x-intercept on the graph, find an x-intercept, and use that for your synthetic division. This one I think we're going to factor into a 3x and a 2x. We'll get a 1 and a 1, and they both need to be negative, so they add to -5 and multiply up to +1. And that will be our answer to the first bit. Should also say on a graph, if you have a function, any place where the graph crosses the x-axis, that creates what's called a real 0. So if we had a dot there and there was an x-intercept there, we'd have one real 0. If we had a graph that's kind of like a cubic shape where it's doing like that thing, we have 3 x-intercepts. So in this case, we would have 3 real 0s. And there should be a homework question kind of asking you about some real 0 stuff. And you're basically, where your x-intercepts are, that tells you how many real 0s you have. Okay, next thing we want to notice. We want to notice that x to the 4th, x to the 6th, x to the 8th, etc., x to the 10th, these all these graphs shapes, they all kind of look like a parabola that's sort of widened out along the bottom a little bit. They will all pass through the point -1, 1 and +1, 1. Let's go back to Desmos to kind of see that. So let's say that we looked at x to the 4th, look at x to the 6th, look at x to the 8th. Oops. And we can kind of see they all have kind of that parabola shape, but they widen out a little bit. And the higher the power, the wider they get along the base, and the steeper they rise when they get done. But they all pass through the point -1, 1 and +1, 1. So we want to note that, and we also want to know if you have x to the odd powers, all those graphs will look kind of like a cubic, but they hang out a little bit longer along the x-axis. So if we kind of go back to Desmos just to kind of see those graphs, what do they look like? We have, say that this was 3rd. Whoops, that's not how I wanted it to be 3rd. This one here, let's say it was to the 5th. This one here, let's say was to the 7th. we can see they all kind of have that basic shape to them, and they all pass through the point -1, -1, and +1, +1. So why we care about that for this section is if we were asked to graph the following things. So for this example, say for part A we wanted to graph f of x equaled -x plus 2 to the 6th minus 1, and part B they want us to graph f of x equals -x minus 1 to the 7th plus 2. We could do this based on transformations. For part A, our starting graph would be x to the 6th. So that would be this basic wider parabola. This would do an x-axis reflection, so that would reflect it where we have our wider parabola, but now it's opening downwards. And then we could move it left 2, down 1. So we would say, all right, left 2 units, down 1 unit, and now we have our wider parabola that opens downwards. And that would be our answer to part A. So we're just using the transformation stuff of x-axis reflection. This moves me left. This moves me down. And the graph I'm scooting around is one of these kind of U-shaped graphs. So for this one, we got a y-axis reflection. We're going to move right 1, and we'll move up 2. So our graph, starting graph is x to the 7th, so that one kind of looks like one of these types here. We do a y-axis reflection, so that reflects the left-hand side is now on the right. The right-hand side's on the left. We move it right 1 and up 2, so we'll say, all right, move that shape around, right 1, up 2 units, and then we kind of have our wider cubic shape. So the point is, with some of these powers of x's, you can use the 2.7 transformation to graph some of these higher powers. So I guess we could say the point is you can use 2.7 transformation stuff to graph if they have the right form. So this is kind of an example of how to do it when you have the correct form. When we have some of these other forms that are not in this format here, then we're going to have to graph them a different way, and that's what basically the rest of the section is going to focus on. So we're going to cover something called end behavior. So what end behavior does is this basically shows what the graph does as it's leaving the viewing rectangle. So this is going to be based on the degree of the polynomial and whether the leading coefficient is even or odd. So we'll say degree even, and we'll say leading coefficient. We'll just say lead coefficient. Leading coefficient positive. If your even degree and the leading coefficient is positive, both your arrows for end behavior will point up, which means as the graph leaves the viewing rectangle, both arrows, it'll leave it with both arrows pointing upwards. If your degree is even, but your leading coefficient is negative, then both arrows point down. If your degree is odd, and your leading coefficient is positive, then your left arrow points down, your right arrow points up. If your degree is odd, and your leading coefficient is negative, then the left arrow points up, and the right arrow points down. So these are kind of 4 cases that you'll bump into with end behavior. So what we're going to do in this next example is we're going to just figure out what's the end behavior for a couple of things when they're in the non-factored form. And then we'll figure out what's the end behavior when stuff is factored. And after that, we'll move on to zeros and multiplicities. And then we'll put it all together to graph some of these. So some of your homeworks will tell you guys you need to find the end behavior. So for this example, let's say find end behavior. And we'll have kind of 4 different functions. First function, f of x equals negative 2x to the 5th plus 4x cubed minus x squared plus 3x minus 1. Part B, we'll have f of x equals 8x to the 4th plus x cubed minus x squared plus 2. Part C, we'll have f of x equals x squared times x minus 1 times x minus 3 squared. And part D, we'll have f of x equals negative 3 times x minus 1 squared times x plus 2. Okay, on parts A and B, these are already in the form where they're completely FOILed out, so we can tell what their leading coefficient is. In this case, we have negative 2 for our leading coefficient, so that is a negative leading coefficient. And the degree here is 5, and 5 is an odd number. So we have negative leading coefficient with odd number, so if it's negative and odd, then we get the end behavior is left arrow up and right arrow down. So it leaves the viewing rectangle like that. For part B, we have a positive leading coefficient here, and our power 4 is even. So this is positive even, which positive even has both arrows pointing upwards. Okay, then on part C and D, we have to figure out what is the leading coefficient on those. So we have to think, if we FOILed out, what would create the largest x term from the FOIL. So we'd have this initial x squared here. This x minus 1, if we FOILed it out, the part where you have just the x, we would count that once. And if we FOILed things out, that would lead us to the leading term there. And this x, it's raised to the second power, so if you FOILed it out, this x would create an x squared, and that's the other one we want. So our leading term here is x to the 5th. It's x squared times x squared. This is positive leading coefficient, and it's odd. Positive odd is left arrow down, right arrow up for end behavior. This one, we got a negative 3x out front. This x would count twice, so that's times an x squared. This x here would count a single time. So this would be negative 3x to the 4th for its leading coefficient. So that's negative even. So this is negative, and that is even. So both arrows would point down because that's the end behavior for the negative even case. Okay, so that's a couple different formats figuring out the end behavior. So next what we want to do is we want to talk about zeros and multiplicities and what shapes graphs make. So if we had a function for this example, say we had f of x equaled x cubed times x minus 4 squared times x plus 1 to the 3rd. Let's say we want to list the zeros and their multiplicity. So each factor, if I look at the internal part of each of these factors, each of these values here will create a 0. So if I think about it, x by itself will make a 0 when x itself is 0. X minus 4 is 0 when x is 4, and x plus 1 is 0 when x is negative 1. So the zeros here are going to be 0 from the x cubed term. X minus 4 is 0 when x is 4, and x plus 1 is 0 when x is negative 1. The multiplicity, this refers to the powers that the factor that create the zeros are raised to. So 0 has multiplicity 3, because the factor x that created the 0 is raised to the third power. X minus 4 created the 0 at 4, it has multiplicity 2. And x plus 1 has a 0 at negative 1, it's to the third power, so its multiplicity is 3. So this is how you extract the zeros and multiplicities. What this tells us is if we had a x-axis and a y-axis and we had an x-intercept, if your multiplicity is 1, then your graph will pass straight through either from top to bottom or from bottom to top. The graph will cross straight through at that particular x-intercept. If the multiplicity is 2, 4, or 6, the graph will come down and it'll bounce and reflect off at the 0, or it will come up from the bottom and reflect off. If your multiplicity is 3, 5, 7, etc., 9, then you'll either come up and make this kind of cubic shape as you cross through the 0, or you'll come down and you'll make kind of the cubic shape as you cross through the 0. So to kind of summarize that, this is based on what the multiplicity does. If your multiplicity is 1, then your graph will just cross straight through at the x-intercept. If your multiplicity is 2, 4, 6, etc., 8, 10, whatever, then your graph will come down and it will reflect off at the 0, or it'll come up from the bottom and it will reflect off at the 0. Then we say, what about if the multiplicity is 3, 5, 7, etc.? So your graph will either come up from the bottom and make kind of this squiggle shape as it passes through, or it will come down from the top and make this little shape as it moves on through. So the end behavior tells us where our graph starts and stops. The multiplicity tells us what shapes we make as the graph crosses through at different zeros. So now we're going to go through and we're going to graph a couple of polynomial functions. And this will kind of put all the 3, 4 stuff together to do this, to build these graphs up. Okay, so let's say for this example, we want a graph. We have f of x equals negative x squared times x minus 1 times x minus 3. Okay, so first of all, I need to find the end behavior. So I have a negative x squared up front. This x counts once. This x counts once. So this will be negative x to the 4th. That's negative even. Negative even, both arrows point down. So this is our end behavior. Next up, we want to find the zeros and multiplicities. So we'll put z for zeros, we'll put m for multiplicities. The x term is 0 at x equals 0. Since it's squared, it has multiplicity 2. This x minus 1 is 0 at 1. And since there's no power up here, its multiplicity we could say is 1. And x minus 3 is 0 when x is 3. And its multiplicity we could say is also 1. The last thing we need is the y-intercept. So to get the y-intercept, we set x equals to 0. Then we'll have all the framework stuff we need to graph this. So we'll have negative 0 squared times 0 minus 1 times 0 minus 3. This is negative 0 times negative 1 times negative 3, which 0 times anything is 0. So we end up with our y-intercept being 0. So we're going to put all this stuff on the graph now, and we want to try to build our graph up. So The zeros tell me x-intercepts of my graph. So my zeros here, these tell me x-intercepts. So I have an x-intercept at 0. I have an x-intercept at 1. And I have another x-intercept out here at 3. My y-intercept is at 0, so I've already placed that. And then the end behavior, I'm going to say my graph comes in from the left of the zeros, and it's going to leave to the right of the zeros. So we got the graph coming in from the left of the zeros, leaving to the right of the zeros. So what I use now is I use the multiplicities of each zero to see what sort of shape to make as I pass through it. The first zero I'm going to bump into is the x-intercept at 0, which has multiplicity 2. So my graph's going to come up and it's going to reflect off, and since it's multiplicity 2, I'm going to make this sort of shape at the x-intercept. In this class, we can't really tell how far these turn around before they come back, so we're just going to move back down and say it turns back around and heads back to the next intercept. So this intercept here is at 1. It has multiplicity 1. When your multiplicity is 1, you pass straight through. Again, without calculus, we can't really tell how high this is going to go. So we'll say it turns around maybe here, and it heads back down to finish off. The last zero is 3. 3 has multiplicity 1, so we pass straight through that 0 as well, and we meet up with our end behavior. And this will be a rough sketch of what our graph looks like. Again, without calculus, we don't really know how low that's supposed to be and how high that's supposed to be, but this should give us the general idea of what the shape looks like, along with what the x-intercepts are and what sort of shapes you make as you cross the x-intercepts. So we're going to do a second one that looks kind of like this, and then we'll do a type where it's instead of being in the factored form, you have to get it in the factored form, and then we'll look at like one or two last ones where you kind of get a type where you have the graph and you have to decide what case works, and we'll talk through that because you'll see one of those in the homework, I think. So next example, let's do another type like that. We want a graph. This time we have -2 out front. So let's call it f of x. So we have a -2 out front. We have a x plus 1 to the third power. And we have an x minus 1 squared. So we want to graph this expression here. So first we need the end behavior. So to get the end behavior, we have the -2 here. This x is going to count 3 times, so we'll get times x cubed. Times this x counts twice, so that'll be x squared. So we get -2x to the 5th. This is negative. 5th power here is odd, so negative odd is going to say left arrow up, right arrow down for our end behavior. Kind of check back to the chart to see that that's the case. Next up, we want to make the table of zeros and their multiplicity. So -2 doesn't create a 0 because there's no x with it like there was in the first one. X plus 1 is 0 at -1. And since the x plus 1 factor is cubed, its multiplicity is 3. X minus 1 is 0 at +1, and its factor is squared. So that's our table of zeros and their multiplicities. So last, we need the y-intercept. To get the y-intercept, I replace the x's with zeros. So I get -2 times 1 cubed times -1 squared. So that would be -2 times 1, which is -2. So my x-intercept is, x-intercept's basically -2 at this point. So to finish this one out, what we do is we put all this information together on our graph. So for our graph, we say, have an x-intercept at -1, have an x-intercept over here at +1, y-intercept's down here at -2. The end behavior is left arrow up, right arrow down, so left arrow is up, and right arrow where it leaves the graph is going to be heading downwards. So my graph comes in and I approach the first 0 at -1. Negative 1 has multiplicity 3, which means I need to make this kind of cubic shape as I pass through there. Let's try it again. I'll make the cubic shape. Pick up the y-intercept and I turn around. I approach the second 0. The second 0 has multiplicity 2. So I need to kind of reflect off and make that U shape, and then I head down to reaching with the rest of my end behavior. And so something like this, I can't get that line to join up. That other line, something like this would be a example of that graph. So, okay, we graphed that one. Got what we wanted there. The next one that we look at is they want us to graph, for this example, say we had f of x equaled 2x cubed plus 5x squared minus x minus 6, and they want us to graph it. So we don't know what the graph of this looks like. If we knew what the graph looked like, we wouldn't have to graph it because we'd already have the graph. So in this one, we need to do the P over Q thing. So we need to get the factored form to figure out the zeros and the multiplicities. Like where it's at right now, we can tell that the end behavior, we'll say EB for end behavior, it's positive odd. So we know the end behavior is left arrow down, right arrow up. We also know the y-intercept. If you put 0 in for the x's, all the terms with x's go away. You're left with the negative 6. That's my y-intercept. So from this form, I can get the end behavior and the y-intercept. The problem is I need to factor it to get the zeros and multiplicities. And in order to factor it, I have to do this P over Q rational zeros theorem. So P is negative 6, Q is positive 2. All the factors of negative 6 are 1, 2, 3, and 6. All the factors of 2 are plus minus 1 and 2. So we're going to generate our P over Q list, which are going to be lists of numbers to try that might work out with synthetic division. So we get 1 over 1, 2 over 1, 3 over 1, 6 over 1, 1 over 2, 2 over 2 is 1, which we already got, 3 over 2 that we need, and 6 over 2 is 3. We already got 3. So this is my list of numbers to try. I'm trying to factor this polynomial. So I'm going to start with the easiest number first, 1. If that doesn't work, I'll move on to negative 1, then 2, negative 2, 3, negative 3. And I'll work my way down the list till I reach all of them, unless I find one with zeros that work. So I bring down 2. 1 times 2 is 2. 5 plus 2 is 7. 1 times 7 is 7. Negative 1 plus 7 is 6. 1 times 6 is 6. And negative 6 plus 6 is 0. So we got really lucky. The first number we tried gave us 0. So this tells me that whenever I go to write the factored form, since I had a 1 out front, I have an x minus 1 factor. This is no x. This is x to the first power. This is x squared. So I get 2x squared plus 7x plus 6 out here. And so what I get here is f of x equals x minus 1. We have times a 2x times an x. And this is supposed to end up being a 7. So 2 times 3 makes a 6. Since the outer, the 2x will hit the 2, that'll make a 4x. 4x plus 3x makes 7x. This is going to be how this particular one factors. So when we go to get the zeros and multiplicities, for zeros, we think what x value makes each factor 0. So x minus 1 is 0 at 1. 2x plus 3, it may be kind of hard to see what makes that one work. So we're going to set it equal to 0 and just solve it for x. So that tells me that negative 3 halves is the x value that would make that expression 0. And x plus 2 would be 0 at negative 2. Since none of these have powers up here, these are all kind of multiplicity 1, which if we go back and think about what does multiplicity 1 mean, that means we're going to pass straight through at each of these. So end behavior, left arrow down, right arrow up. Y-intercepts at negative 6. Have my zeros and multiplicities. Let's put it all together. Try to graph it. So zeros at 1. Zeros at negative 1.5. A 0 is at negative 2. Y-intercepts down here at negative 6. Left arrow down, right arrow up from the end behavior. So I approach the first 0, and it's multiplicity 1, so I pass through. Turn around, pick up the second 0, it's multiplicity 1, so I pass straight through, get my y-intercept. Approach the last 0, it's multiplicity 1, so I just pass straight through, meet up with the end behavior. And that would be an example of how the graph works. So setting up a little bit of information for the final type. You may have some where it's a multiple choice and they'll give you a graph. So they say, given the graph, which function could be the graph, I guess. So if you have a graph, like say they give you a graph like this and they give you a multiple choice and they say, hey, which of these functions could have that as a graph? Here's kind of the process to do that. First, check end behavior. And what you'll do is you'll mark out any that have the wrong end behavior. Second, you can get the zeros and multiplicities. To get the zeros, use the x-intercept of the graph. And for multiplicities, check the shape at the zeros, or at the x-intercepts, I guess you could say. And you'll throw out any with the wrong x-intercept or wrong shape due to multiplicity. If you still haven't gotten down to just one of them, so it's like one of them telling you, so again, this would be like a multiple choice problem. So if you're given a graph and they give you multiple choice of which of the functions could be the graph, check the end behavior, and of your choices, mark out any that have the wrong end behavior. Then get the zeros and multiplicities, throw out any that have the x-intercepts in the wrong place, or throw out any that have the wrong shape at an x-intercept. And then the last thing, if you need to, check y-intercepts. And that should be enough to narrow it down. If it really isn't, if it still can't tell, then you can check checkpoints at the very end. But most of the time, most of these multiple choices, once you get kind of the zeros and multiplicities, usually you kind of know which one it is. Occasionally you have to go and check y-intercepts. Occasionally you may have to check individual points. So we'll stop there for stuff and call it a day.